Alright, this example problem is for elastic potential energy. We could actually end up doing a whole lot more than just elastic potential energy with this problem. However, I just want to show you what's relevant to what you're learning in the slides at this point. Okay, pretty big problem. We're going to need to draw a diagram to make some sense of it. Okay, we got a 70-kilogram stuntman that's attached to a bungee cord that has an unstretched length of 15 meters. He jumps off a bridge spanning the river from a height of 50 meters. When he finally stops, the cord has a stretched length of 44 meters. Treat the stuntman as a point mass, disregard the weight of the bungee cord, and then assuming the spring constant of the bungee cord is 71.8 newtons per meters, what is the elastic potential energy of the bungee cord when he stops falling? Blah, mouthful. Most people jump off a bridge just like it says. So I'm going to say, here's the bridge. Okay? Alright, it says that it spans a river from a height of 50 meters. I'll say this height here is 50 meters. Here's the river. Okay. Alright, it says that he's got a bungee cord attached to him that normally is 15 meters long, so I'm going to draw the little bungee cord and say, which this is not anywhere to scale, well, it's close enough, kind of. Okay, that this is 15 meters. That's the unstretched length, but when he is on it and he jumps off, it stretches out to 44 meters. Then he's here. That's the guy. Okay, so this distance is 44 meters. Okay. Alright, it also says that he has a mass of 70 kilograms. Right? Another piece of information they give us, so far I've used the 70 kilograms, I've used the length of the unstretched cord, the height of the bridge from the river, the length of the stretched bungee cord. I'm still left with the spring constant. So I'm going to go ahead and put the K, which is the symbol for spring constants, lowercase k. Alright, that is equal to 71.8 newtons per meters. Okay. Now here it says, what's the elastic potential energy? So it says, what's the elastic potential energy? I'm just going to put PE with a little e for elastic and write out the equation. So the equation is 1/2 times the spring constant times the displacement squared. And this displacement here is really the displacement of the spring. It's the amount stretched or compressed. Okay. Alright. So they give us a lot of extra information. Okay. I don't need to know mass for this problem. Okay. I also don't need to know the height of anything that's not the cord itself, right? Because the only thing that I need to know any length for or whatever is the amount that that cord has stretched. Okay. So I don't need this information for the problem either. Okay. Instead, I need to know its relaxed length and its stretched length in this case. And that x is the amount that it was stretched or compressed. So x is going to be the difference between these two lengths. So this here would be x. So I can solve for x by taking the difference. Okay, and it's really, you can do the absolute value of the two because it's just the number stretched. It doesn't matter if it's positive or negative, because if you square anything, whether it's positive or negative, the answer will be positive. So take the absolute value, it's fine. Or just take the biggest number and subtract the smallest one from it. Okay. So if x is 44 minus 15, that's going to give us, what, 29? It's late. Yep. Hey, so my brain does work, I just don't trust it. So 29 meters. So it was stretched out 29 meters. This is its original length. That's its final length. It stretched 29 meters. Okay. So now I can plug everything that I need into my equation. Elastic potential energy is equal to 1/2 times my spring constant, which is 71.8 Newton per meter, okay, or newtons per meter. That's the amount of force required to stretch or compress it by 1 meter. So it makes sense it's force over distance. And then times this stretched, in this case, this stretched length, 29 meters squared. Okay. So remember, this square has to go to both the unit and the number there, so I'm going to rewrite this. Not gravitational potential energy, just kidding, that's elastic potential energy, is equal to 1/2 times 71.8 newtons per meter times 29 squared, which is 841 meters squared. Okay. My elastic potential energy then is going to be 1/2 times 71.8 times 841. Okay, so basically 30,000. Okay, and let's look. We get Newton meter, or Newton over meter times meter squared. So this meter is going to cancel out one of those, and we're going to end up with Newton times meters. That's a joule. Okay. You could leave this like this for my class. 30,000 is fine. If you are a stickler for significant figures in this moment, we would need 2 sig figs based off of what all. Oh, just kidding. I didn't even keep sig figs here. 3 sig figs. So you would write this as 3.00 times 10 to the 4th joules. But really, 30,000 joules is totally fine with me.